about that. So this is the webinar. Like say, it's basic water treatment. It's a pretty age 2 hours. So I'll be the one conducting this. So the here is the outline that we'll go through. Introduction will introduce a little bit what is the meaning of the water treatment. Then the coagulation flocculation will be the basic part of it. Softening process. Reactors will define the reactors. Mixing and flocculation will be another option. Uh, and so on. Okay. Um, then filtration. Filtration is a basic part of the treatment process. Then disinfection. We'll discuss a little bit of disinfection, then absorption process, a kind of advanced treatment process, then water plant waste management. So this would be our topic for the discussion today. So here are the learning outcomes from this topic today. We'll get it. A participant will be able to explain the water chemistry. So that means definitely chemistry is involved in order to do the water treatment process there. We'll have to know the chemistry, chemical equations and other things, how the reaction happens and other things like that. Then discuss the reaction kinetics, water quality and water quality standards. Describe the concept of coagulation, flocculation, water softening processes, sedimentation, filtration and absorption. Design the unit processes for water treatment. We'll try to design, do a couple of design examples based on whatever we discussed or whatever we learned there. So under the introduction, so what we'll do, like we'll introduce like water chemistry, reaction kinetics, water quality. There are 4 different parts of the water quality. Could be based on the characteristics, physical, chemical, biological, and radiological. Then we will discuss the water quality standards, water classification of treatment systems, and things like that. So under introduction, first thing that we usually do or we need to know is different types of water supply system. So the first one that I have here by definition is a public water system, PWS. Provide water for human consumption through pipes or any other, the pipe is the only option. So for 15 service connections or 25 people, 60 days per year. So this is the definition of PWS. Things like that. Okay, so let me see. I don't see the participant list over there, chat list or anything. I'll keep it in the sidewise so I can see if anybody asks any questions. So somebody says slides are not moving. Do you see the slides moving now? You let me know. So this is the first definition, public water system. That means slides are not moving. I don't know. It's moving from my side. So how about, so that means sharing didn't work, right? In this case, sharing didn't work. Resume sharing. Okay, how about now? Okay, so now you can see it. Okay. Okay, good. So sorry about that. We started from here. Then so these are the outline. These are the outline that I said: introduction, coagulation, softening, reactors, mixing, sedimentation, filtration, disinfection, absorption, and water treatment. So these are the one participant will be able to explain the water chemistry. These are the learning objectives or learning outcomes. Yes, I can do that. I will share all the slides by email. I think I'll send it to Hisham and he can do that. Or if you send me your email address, I can do that too. So at the end of this slide, at the end of the presentation, I think my email address should be there in the last slide. So I'll show you that one. Okay, so these are our learning outcomes for this topic today. Then under introduction, these are the things we'll be discussing. And under that introduction, we started already this slide. So in this case, the first definition is public water system, PWS. The second one is community water system. So a public water system that supplies water to the same people or population year round with the community. And the public means like say 15 service, excuse me, 15 service connections, 25 people at least 60 days per year. Then this is called the PWS. And out of the PWS, community water system is the one that supply water to the same people throughout the year. Like say any subdivision, whenever we have any water supply, we call it community because this subdivision or couple of subdivision may have the same services and other things like that. So I have the video here. Video doesn't work because I had something the community water area. I think it's some small video, but it doesn't work. I think now because they changed the location of things like that. But anyway, non-transient, non-community water system, the public water system that regularly supplies water to at least 25 people, same people, at least for 6 months, but not year-round. Then it's called non-transient. The next one is the transient. So here are some of the examples: school, hospital, office, factories, and so on. Transient one is transient non-community water system. So a public water system that supplies water in a place such as gas station, campground, but people do not remain or for long period of time. So these are different types of definition of the water supply system, right? Water system. So here is the classification of the water systems. So number one is very small, that serve only 25 to 500 people. Small water system means like say 501 to 3,300. The medium one is the next one that can serve up to 10,000. Large one can serve up to 100,000. The very large one is more than 100,000. So the main reason the EPA classified those because of the regulations and reporting requirements. So the main idea of those things was like, okay, if I have a 25 to 50 people, 500 people, we want to make it very stringent because it may not be, if I make it very stringent, ask them to do sampling every 2 hours and report every day, then it could be too much burden. They may not even survive, right? Whereas the other one, very large one, we can ask anything because they will have enough money to enough people, enough revenue. So that's the main reason, and we can enforce more regulation to them. It doesn't mean that the smaller one will have an issue and people will die. No, it's not the case. But again, due to the management point of view and reporting point of view, it was different. So that's the reason they did the classification based on the size of the number of people they serve. Okay? So there are basic definitions that we should know going forward for this topic. Pathogen, an organism which causes disease. Potable water means safe to drink. Safe means if we drink it, then it will not die. Palatable means pleasant to drink. That means it's not colored, brown, or anything like that. And the other definition is the wholesome water. Wholesome water and palatable, safe are very close. Only difference is unpolluted, free from toxic substances, as well as excessive amounts of mineral, organic matter that may impair the water quality. So that was the main idea. Okay, so there are a little bit of difference between the wholesome water, pollutable, and potable water, right? Things like that. Now the question is why we make water palatable, that says pleasant to drink. It's definitely people's psychology, meaning if I see a color water, most likely our mentality is we would like to drink water that is kind of crystal clear, right? Things like that, other than Coke or Fanta or Sprite, not the Sprite, Fanta or other things. So if it is the water, then we would like to see very clear one. It makes sense because if we have some kind of suspended materials or even dissolved, it will be colored. So we don't feel comfortable drinking that. That's the reason we have to make the water palatable. So palatable by definition is palatable means pleasing to drink, right? By definition. Then we have to know, like say, how we can measure the pollution, contaminants in there. So in the water area, definitely we do milligram per liter. That means mass per unit volume of the water, the mass of the contaminants per volume of the solution in this case. The other stoichiometric calculation that we use is called molarity and normality, right? We understand the molarity and normality. Then the other one we use is called percentage. Like say 10% pollution means like say 10 milligram would be the weight of the pollutant in there. If we have a 100 liter of the solution, right? 1 liter of the solution, 10% or 100 milliliter of the solution, or whatever we call it. So that's the equation number 1. Okay. So I have a little more description here how we get it. Then parts per million is the another one. Sometimes chemical concentration are put in ppm. Basically, ppm and milligram per liter are the same if we know the density of water and it is close to 1 gram per milliliter, or sorry, gram per cc or gram per milliliter. Okay, so in this case, then 1 milligram per liter is equal to 1 ppm. I have the calculation over here. I started with 1 milligram per liter, then I did the conversion with the chart here at the grid method. This is we call it grid method. Then I have a 1 milligram per 1 million milligram. That's why it's called parts per million. It could be done under the call of what is called the volume, or it could be mass. It could be mass wise or the volume wise. Okay. So anytime you guys have any question, you can speak up or raise your hand. I don't think I can see your hand maybe. If I click on the participant, maybe I should say that. But anyway, you can probably type it there. Okay, typing would be better. I have it open. Yeah, please use chat. Chat is good. Okay, so this was the mainly how we can convert ppm to milligram per liter and milligram per liter to ppm. Ultimately, they are the same, and the definition of parts per million. So in here, I'm trying to discuss a little bit of percent. So if I do the percent looks like the 1 milligram per liter. 1 milligram per liter becomes almost like, say, what? 0.0001%. That means 1% equal to 10,000 milligram per liter. This is another relationship. Okay, 1%, if I say 1%, means it would be 10,000 milligram per liter in this case. Okay, 1%. So that's the way we convert it. And the next thing that we have to know, what is the molecular weight, atomic weight, and equivalent. Atomic weight, I don't have it here. Atomic weight is like, say, for oxygen. If oxygen, I say molecular weight would be 16. But if I say the atomic weight is 16. If I say molecular weight, then it would be 32. Why? Because 2 oxygen, like say, atom can make 1 molecule, O2, right? We know that. So that's why molecular weight or atomic weight is the main, like say, make more appropriate sense in here. But usually we do the molecular weight, because 1 molecular weight per liter of the solution is called 1 molarity, and 1 equivalent weight is the basically in 1 liter solution is called the normality. Now, how we can measure the equivalent weight? If I know the molecular weight, so in this case, then the molecular weight divided by number n. N means number of electrons transferred in redox reaction or number of protons transferred in acid-base reactions. So equivalent weight is equal to molecular weight divided by n. Now I'll explain the n values. I have a little bit here. So there are 4 scenarios that n value can be used or calculated. In acid-base reaction, n is the number of hydrogen ion that molecule transfers. And in the precipitation reaction, n is the balance of the element in question. For compounds, n is equivalent to the number of hydrogen ion it requires to replace the cation. I have a simple example over here for calcium carbonate. So in order to replace calcium, I need 2 hydrogen, right? Because carbonic acid, or we can say H2CO3, take 2 hydrogen ions to replace calcium. Therefore, n is equal to 2. In this case, calcium carbonate, for calcium carbonate, n is equal to 2. In oxidation reduction reactions, n is equal to the change in the oxidation number that the compound undergoes in reaction. Okay, so like say how many plus minus in the top, right? Oxidation reaction. So you guys know that. Okay, so here are a little bit more description of the molarity. 1 mole is 1 liter. How can we convert from molarity to milligram per liter? So this equation will help us. Equation number 7. If I have a milligram per liter, can be written as molarity times molecular weight times 10 to the 3. And I'm going to explain here. Molarity is moles per liter, right? Then the molecular weight is gram per moles, and then this is Since it is like say mole cancel out, gram per liter. So if I would like to convert into milligram per liter, then I have to do 1000 milligram is equal to 1 gram. If I do that, then ultimately this is the equation becomes. This is the molarity, this is the molecular weight, and this is 10 to the power 3. I will turn out to be. So if I know the molarity, then I can multiply with the molecular weight and 10 to the power 3 to get the milligram per liter. And from milligram per liter, molarity can be calculated easily. Milligram per liter divided by molecular weight divided by 1000 will give me the molarity. So that's how we can convert each other. And normality is the equivalent weight per liter of the solution that I explained before. So normality is basically molarity times n, if we know the n value for the compound or whatever the solution we are dealing with, contaminant we are dealing with, then we should be able to find the normality of the solution. So you guys know that the normality of the solution we use a lot in the lab and other technical areas, what normal solution or molarity solution we use and other things like that. As I mentioned, the water chemistry, a little bit of review of few things. So mainly chemical reactions led to water treatments are part of the water chemistry. Fundamentals of water chemistry necessary to understand water quality, monitoring, assessment, and treatment. So some of the physical properties like density, right, mass density, specific weight, specific gravity, dynamic viscosity, and the kinematic viscosity. These are the ones. Some cases we'll be using those in a problem solving, especially designing. Designing field here and there, we should be able to use those. So these are just kind of review for our purpose of understanding. Here are some of the definition that I mentioned. So these are just the definition. Over there, I just mentioned the what is called like physical properties. Here I'm defining those. Okay. So chemical reaction, there are 4 types. Chemical reactions. The one is precipitation. Precipitation is nothing but if we make a reaction in 2 different chemicals, so something maybe becomes solid there and solid in the bottom is called the precipitation. Solubility of complexes in water is another way to define the precipitation. Acid-base, low pH solution, we call it acid that release protons, and the base is high pH, accept proton. So one can release proton. When it releases the proton means what? Ultimately, it becomes more negative, right? And when it accepts the proton, it becomes more positive. Electron and proton, right? Things like that. The ion association, dissolved ion can react with each other and form a solid compound or may exist in water complex with other ions. So this is association. Because otherwise, we can say ion association, different ion can be combined together to do the electrical neutrality and things like that. So here are more oxidation reduction, a little more description. An atom molecular ion is said to undergo oxidation when it loses an electron, means it becomes positive, like metals, right? And when it undergo reduction when it gains electron, meaning negative ions, right? Making negative ions. And oxidation reduction, I just add a little bit more here. There's a lot of chemistry. Probably we don't need to go through all of those. These are some of the examples that I might have here. We'll be using later on those things. Okay, then buffer solution, the solution that prevents changing the pH very quickly. It could be either way, going up or going down. Alkalinity is another measure of the oxygen neutral capacity or something like that. The sum of tritratable bases down to the pH of 4 in most water. The only significant contributing property are carbonate species and any free hydrogen and hydroxyl ion. The hydrogen ion that can be taken up by the water approximately carbonate species is this. So this is the mathematical definition of alkalinity. Alkalinity, another way, acid neutralizing capacity, ANC. Meaning if we have an alkalinity, then if we add a lot of acid over there or something, that means the pH will not go down that much. That's the main idea of the alkalinity. So alkalinity is a capacity that even adding some kind of acidic solution to a solution, it will prevent lowering the pH very shortly or very abruptly. So it's very important for us because certain cases, if we do the water treatment and the pH goes down very quickly, then we have to do something else to bring the pH up. because the requirement for the pH for drinking water is 6.5 to 7.5. So in order to keep up with that, so this would be an issue. I'm going to show you a couple more like say reactions over there that will tell us like if we don't have enough alkalinity in the water, then what's going to happen. So I'll show you this. And by definition, alkalinity is a part of bicarbonate, carbonate, hydrogen ion, and the negative of hydrogen ion. So in this case, these are the three contributors in alkalinity: bicarbonate, carbonate, and hydroxyl ion, right? Hydrogen ion is the one other way around. So in our cases, if we consider pH is equal to 7, pH is equal to 7 means hydrogen ion is 10 to the minus 7. So pH plus POH is equal to 14. So these two can be together 10 to the minus 14. So if this is 10 to the minus 7, this has to be 10 to the minus 7, right? So in this case, they are equal and they cancel out. So main two components that contributes to the alkalinity are the bicarbonate and the carbonate. So that's why my definition over here will change a little bit. In most neutral water, pH is 6 to 8. Hydrogen ion and hydroxyl are negligible, such that negligible in the sense they will cancel each other, right? Because they are a very small amount. So that means the alkalinity would be basically bicarbonate and 2 carbonate. So carbonate is multiplied by 2 because it can accept 2 protons. That's why -2 right there, right? The other one is only 1, that's why. The pertinent acid-base reactions are this. Carbonate can go hydrogen ion and carbonic acid, right? Is CO3. And bicarbonate, I think we call it bicarbonate. The bicarbonate again can undergo two certain reaction, acid-base reaction, and become carbonate. So the pH pKa1 is at 6.35, PA2 is 610.33. These are equilibrium constant, right? Ka is the equilibrium constant. Our pK equal log Ka, and K is called the equilibrium constant, meaning that constant which or the reaction rate constant at which there will be no more product will go back to the reactant, or no more reactant will go back to the product. Conversion will not be happening anymore. That's the idea of this. So few things that we need to learn about here. One is called the reaction kinetics, how the reaction works, because whenever we are doing the treatment, we're changing from one to another, right? Or we are reducing what is called we are reducing the like the contaminants concentration over here. Okay, so the study how the chemical reaction proceed with time is called the reaction kinetics. Rate of reaction, the rate of formation and the appearance of a compound is called rate of like reaction. Homogeneous, take place in a single phase. Single phase means just the first time if you do the reaction, whatever the amount needs to be converted to, they will convert it to the whole reactant to the product. Heterogeneous means take place in multiple phases, solid, liquid, and gas, 3 different phases. Order of reaction, sum of the exponents in the reaction rate equation. So it could be 2, 3, 4, it could be 1, 2, 3, 4, whatever the reaction rate. Order of reaction in this case. So order of reaction, we'll discuss few things here. There are 3 different types order of reactions. One is called zero order kinetics, other one is the first order and the second order. In the zero order kinetics, what it means that the reactant we have will be a product, right? P. So using C to represent the concentration of A at any time T, the disappearance of A with respect to time is dC over dt is equal to KC0. So in this case, basically this concept is dC over dt is proportional to C0. That's why it's called the zero order kinetics. Whenever its power is the C0. Then we got a K, negative K. So negative K C0, or we think like that. We can think of that. So in this case, why it is negative? The negative sign comes basically for the purpose of showing that the concentration is going down. It's not going up. If we see positive, that means with the time, the concentration of the contaminants is going higher, it's increasing. That's why the negative sign is. In order to make the reaction work for us, we have to make the K value negative because our intention is to make the concentration down. So that's why it is. Now, in this case, we can do the integration a little bit. If we do the integration, the equation becomes C equal to C0 minus KT. So here is the equation, right? This is C0 is here, initial concentration of the contaminant. This is the time. K is a negative here, means it would be theirs. The slope would be negative K. So that's why this is the line represent the zero order quality. Now, why do we use it? Certain cases in environmental engineering, I have seen that it's very minimal use of it. But for the purpose of understanding it, we are discussing it. So mainly, the one that is widely used is the first order kinetics. Okay, so first order kinetics would be the main one. So let's go to the next one. Next one is the first order kinetics. So reaction proceeds at a rate directly proportional to the concentration of one reactant. Okay, it represents a curve in normal graph paper, but linear to the semi-log paper. If it is considered that a single reactant converting to a single product, A to P, A is the reactant, P is the product. The change in the concentration C of A with respect to time is dC over dt is proportional to C to the power 1. Then if we replace the power 1, then it becomes like say minus Kc. Proportional constant is not, K is the proportional constant. Negative again, why the negative is? Because it will change with the time. It will decrease with the time. Change means it will decrease. So now from this equation, we can go and do a little bit of like say integration. So integration would be like that. Ultimately, C equal to C0 to the minus KT. This would be the equation for that. And if I take a log and T, then let's do this, then this is the equation. If we do the logarithm, that is like that. So straight line sometimes is important if we need to know the value of K, then from the lab data, so then definitely you have to do this. You cannot do this one because we don't know how to calculate the value of K from this, but we know how to do it from that, right? So this is the first order kinetics. As I mentioned that the first order kinetics is the widely used one in environmental engineering, in water and wastewater treatment areas, even disinfection. Second order kinetics is basically reaction process at a rate directly proportional to the second power of the single reactant being converted into a single product. So in this case, 2 A equal to P, right? So that means 2 power in this case. dC over dt is proportional to the C square. So ultimately to negative K C square. And if I do the integration using the boundary condition or initial condition, I think just one condition is fine. So then the equation becomes 1 over C minus 1 over C0 equal to KT. So if I plot this one here, 1 over C, this side, this over T, then this will give me 1 over C0, and initial opposite of initial concentration, then this will be the my curve, right? This is my straight line. This will be my straight line. So any questions so far? So these are the one mostly we're discussing theoretical part of it, like so that involved so a little bit of theoretical background that we'll be going through in this case. Let me know if I'm going very fast or anything like that. Okay, so water quality, physical characteristics, basically pH, turbidity, suspended solid, color, taste and odor, and temperature. These are kind of physical characteristics. How pH is the physical characteristics? Certain cases, the pH, if we dip our finger, and if it is pH is less than 2, then it will start burning our finger, right? So that's the reason that we can say that, like say, physical means if we have a 5 senses and we can feel with any of the 5 senses, like tasting it, like seeing it, hearing it, or feeling it through the skin, right? Things like that, or smelling it. So these are the 5 senses that we have that we can sense anything, we can feel like that. It fits into these 5 senses, then this is physical characteristic. So pH falls under that. Turbidity, we can see it, right? A lot of suspended materials are there. Color, we can see. Taste and odor, we can put it in our tongue and we can taste it. Temperature, we can feel it. We can see it, but we can, sometimes we can see it. If it is boiling, then the steam is coming out of it. We know that 100 degrees Celsius, right? But but we know that if we dip our finger, it is too cold, then we'll feel that. If it is too hot, then we'll feel that too. So that's what it is. Chemical is very hard to see by any. That's why we have to do some kind of chemical analysis to understand that the chemical properties or chemical qualities. Chloride, iron, lead, all of those are part of the chemical quality. Okay. So then the next one is microbiological quality. So microbiological quality means, like, say, if we have any kind of microorganism, even pathogens that we defined before, then it is problematic for us, right? So that's why we have to know the microbiological characteristics also. So the few things that we do in here, we do the coliform, right? Fecal coliform, total coliform, fecal coliform, right? All of this. So, you know, E. coli, you heard the name E. coli, right? A lot of time they have a problem, spinach problem. I think a few years back they had a spinach problem in the US, right? And I heard even it could be E. coli or it could be salmonella and some other part of it. So these are the one basically we do in the microbiological characteristics in the lab process and other things like that. So why coliform are selected as an indicator organism? There is a debate on that. The coliform itself could be pathogen or could not be pathogen. But the main idea is if the E. coli is there, Escherichia coli is there, then there is a high probability, almost close to 100% probability that there will be some kind of pathogens there. Okay? So that's the main idea of using the indicator organism as a coliform. Excreted in a large quantities, can survive in water, are relatively easy to culture. It means they grow very quick and very fast, right? So that's the main idea of things like that. The next one, or the last characteristics, is the very logical characteristics. The effects of human exposure to radiation or radioactive material are harmful, and unnecessary exposure should be avoided. Humans have always been exposed to natural radiation from water, food, and air. The amount of radiation to which the individual is normally exposed varies with the amount of background radioactivity. So water with high radioactivity is not normal and is confined in great degree to areas where nuclear industries are situated. So in this case, definitely it is important to know if it is like, say, any nuclear waste water nearby and we are even drinking it, then definitely it will be high energy, right? The radiology is nothing but a high energy gamma ray is passing through, things like that. So in this case, we'll be definitely in trouble. So this is another characteristics of water that we should know, very logical characteristics. Then we'll come back to the water quality standards. So water quality standards, basically there are two types of standards. One, we call it MCL, and it came from the National Safe Drinking Water Act, 1974, that was booked by President Ford signed it. So this is the main thing required, that we have to have a water standard to check against anything like that. EPA was directed to establish maximum contaminant levels, MCL, for public water system to prevent the occurrence of any known or anticipated adverse health effect with adequate margin of safety. So there are two types of standard. One is called MCL. MCL, we call it for certain parameters that has a direct health effect. And the other one is called SMCL, secondary. So it means there is no real health effect. Here is the one. The SMCL is the National Safe Drinking Water Act, provided additional set of standards to prescribe maximum limit for those that tend to make water disagreeable, means non-palatable, not potable, non-palatable, not pleasant to drink or things like that, but do not have any particular adverse health effect. Then this is called the SMCL. Okay, these are the title of the type of standard. The other one is called AWWA goals, American Water Works goals. Means this is, you cannot apply, you cannot enforce to people have it, but the goal is, like, so they do a research, a lot of research, American Water Works Association, and submit to EPA. EPA, sometimes they can adopt it. They say, no, we are not adopting it because it's not the time to adopt a new one or anything like that. So that's the main idea. The primary and secondary maximum levels are the maximum allowed. Our reasonable goal, desirable limits, may be much lower than MCL themselves. These are advisable. If you feel like you would like to follow it, then you can follow it. If not, then you are not violating anything. but advisable, if it is seriously advisable, then you should follow it. But if you don't follow it, that's fine. They cannot take you to the court or anywhere like that. So there's the goal. Okay. So standard, we'll divide the standard into 4 categories also, right? Physical, chemical, biological, and other things. We can do that. So the water classification and treatment system. In order to do the classification system, first we have to know the sources. There are 2 types of water sources. One is from surface water, other one is from groundwater, right? So surface water is the mostly available one for us, right? Because it's we have a river, creek, lake nearby, so we can get it very easy. But the problem is, and the groundwater we have to dig somewhere to get. We can get both, right? But the issue is now which one is cheaper for us to get with the healthy things and like that. So it depends on, like, say, we cannot say just, okay, this is cheaper or this is expensive. No, we can say that. It depends on our situation, meaning in this case, where we are getting it from, right? So meaning, so if I am getting it from surface water, meaning from the river, right? Because the river water might have bacteria, viruses, inorganic substances that might have health effects. That means we may have to treat it more. We can get it from groundwater, means groundwater most likely it is kind of pure, right? Pure in the sense means less contaminant, maybe some trace elements of things, but at least there may be some bacteria there, right? Depending on what they are there. So the difference between the 2, surface water and groundwater, surface water may have a lot of what? The suspended materials, right? Suspended materials. And the groundwater will have a lot of dissolved materials, right? So a lot of dissolved material. Now, both of them has effect, health effect, depending on what they are. Now, which one would be easier to treat? Again, the surface water is easier to get, right, nearby, and treat is maybe a little bit expensive. But the groundwater, another thing is, it's not easy to get because we need to dig wells to get it. So that's why groundwater may be, like say, cheaper to treat, but maybe expensive to get, right? So that's what we are wondering. So we cannot just say that this is cheaper, this is better. No, it depends on our situation, where we are getting it from, what kind of treatment is needed, and so on. So that's for both of them. So there is a third source. Third source is called the rainwater source, right? So the rainwater source means there is not a huge source because of main thing is main thing is, like, say, certain areas may not have enough rainfall to start with, right? Enough rainfall to start with. But however, it's not a, that's why I didn't mention it here, because it's not a viable source. It could be a simple source. A lot of people nowadays, they are doing it. They are collecting it from the rooftop and maybe using it for the lawn watering, car washing, and other things like that. So a lot of people, they are doing it. But it's not a viable source or the reliable source for all the time. So here are the treatment processes that I have here in a tabular form. So that would be very good to take a look. A pollutant type, I divided, like, say, different pollutant type. Then parameter to measure in the lab, what do we call it in the lab? Then treatment process or technology, what kind of treatment process we can use to remove those. Suspended or colloidal materials, it can give us stability, color, total solid, and suspended solid, total suspended solid. We can do coagulation, flocculation, sedimentation, filtration. These are the one we can do to remove those, right? Then I'm going to explain what is coagulation, flocculation, sedimentation, and filtration. Then dissolved solids, pH, color. pH means lower level of hydrogen. I think hydrogen ion will give you the pH. Color, okay, again suspended and the dissolved material can give you color, total dissolved solid. Hardness due to the chemical over there, like calcium, magnesium carbonate, bicarbonate. Alkalinity also same. Metals can be dissolved from THM, trihalometane, right? It comes from the chlorine disinfection process. Chemical precipitation, softening, absorption, these are the 3 treatment processes we can do to remove or alter the pH, color, turbidity, sorry, not the turbidity, pH, color, TDS, hardness, percent metal, and pH. Suspended and dissolved solid, suspended or dissolved if we both nutrient, nitrogen, and phosphorus. Chemical precipitation, biological treatment can be done to remove the nitrogen and phosphorus. Another one could be organics. Organics can be represented by BOD5 and COD. So in this case, chemical and biological treatment are the two that we can do to remove the BOD and COD5, right? I think COD5 and BOD5 and COD. The microorganisms or pathogens, so E. coli, tubercle coliform, fecal coliform, salmonella, and other pathogens. So we can name that like that. What we can do to remove those? Ultraviolet ray disinfection by chlorine or ultraviolet ray or ozone. So disinfection is the process that we can use to remove the microorganism, not to remove, deactivate, or kill the microorganism. Things like that. So any questions so far? Okay. So the treatment system that we are discussing, basically primarily three different can be done, or can be categorized. So it would be disinfection to make water safe, filtration and softening, all of those to make the water palatable. Yeah, things like that. So plants employing simple chlorination have a high water quality source and chlorinated to ensure that the water reaching customer contains safe bacterial level or no bacterial level. Generally, filtration plant is used to surface water and softening plant to groundwater. Softening plant usually does like removing the hardness of the water, and filtration basically removes the suspended materials from the water. So that's why filtration is said to be good for the surface water, and the softening process or treatment plant is good for the groundwater, things like that. So any questions so far? Okay. Move forward. There is a little bit more description of the filtration plant. I'm going to show the picture. I'll let them describe here. This is the picture of the surface water with the filtration plant, meaning the surface water coming from river or whatever, then it's mixing, rapid mixing here. Coagulation, flocculation, I'm going to discuss more on that. We do a little bit of, like say, chemical addition over there, mainly aluminum sulfate or ferric chloride in there. Then we, like say, stir it a little bit, mixing them. Then they come back together, smaller particle, bigger particle, and goes here and settle. Then it goes to a rapid filtration system, then disinfection, and goes to storage, then submit to the paper house. Okay, looks like I have seen some question. Would disinfection remove E. coli after good bacteria used for BOD reduction in wastewater treatment? Yeah, wastewater treatment is different. Water treatment and wastewater treatment is different. This process is different. So in the water treatment, we don't really remove the BOD5. The reason is most of the water that we have, then surface water, even groundwater, they have very minimum organic content. So if there is no organic content, there is no BOD5 in there, right? So if we have one or two, but if we do the filtration process, this will go away. We are not doing any biological process. No biological treatment for the water. If we can do it, if we have any phosphorus, nitrogen in the water, we would like to remove it, then we can do it. Otherwise, water treatment process, there is no requirement for biological treatment. Whereas for the wastewater treatment, the biological treatment is important because we have more organics over there. Okay, so that's why, it's important to know that the biological process is not involved in water treatment, and because of there is no BOD. Let me read the question again. Would disinfection to remove E. coli affect good bacteria used for BOD reduction? Okay, this is wastewater. That's what I was trying to answer. Yes, most of the time, when we do the biological process in there, The E. coli is not somebody who helps us to do the process. Like it should be bacteria, virus, and other things. E. coli is a pathogen. It doesn't really help us to remove the organic. But once we finish everything, the E. coli could be still there after the treatment of the wastewater. Then we need to do the disinfection finally before the treated wastewater goes to the river, because we don't want any kind of bacteria or E. coli or anything goes to the river water. So that's it. The next question, would disinfection cause good microbes to die that help the BOD reduction? Yes, it does. That's why in these cases, it's not important for us in the water treatment, but in the wastewater treatment, yes, it is very important. So in the wastewater treatment, we don't use any chlorine or anything before it goes to the aeration tank. Aeration tanks means where the mainly bugs eats the organics, right, as a food or substrate. So you are right on those. Basically, BOD reduction, we don't use the disinfection before reducing the BOD. Very good question, thank you. So here is the other one, the flowchart for the groundwater softening plant. So in this case, what is happening? The groundwater, it could be hard water. We'll define the hardness a little bit later. The rapid mix, then we do the reaction here. Okay, so then pH is 10.3 to 11. The settling tank, it settles because it settles because of the high pH. It settles the calcium and magnesium carbonate and other things like that. Then it goes here. Then we have to recalculation. We don't want that high pH. We would like to bring down the pH to 6.5 to 8.5. Then the rapid sand filter, it goes to disinfection, ultimately goes to the storage, then to the distribution system. Okay, so this is for the groundwater treatment process or flow chart. This shows the SCADA. SCADA means like, so you have a system that you can manage from the computer. It can show different tank height and water level, even concentration to some extent. If you have a probe in there, then you can set pH and other things directly to your computer. Coagulation. So as we mentioned that the first treatment process could be coagulation. So what is coagulation means? Coagulation is a turning to the process by which, like say, the process by which we can bring the colloidal, smaller particle together. Okay, this is the process. The mechanism by which it does is called coagulation, right? So the main objective of the coagulation to bring the smaller particle together and making a bigger particle. And if we make a bigger particle would be higher density is to settle into the water. So as I mentioned, it applies to removal of colloidal particles. Coagulation is a method to alter the colors so that they can be able to approach and adhere to each other and become a larger particle. Larger particle, when they come together, become larger particle, it's called the flux. Okay, this is the definition of the flux. So coagulation is a charge reduction. So I'll explain a little bit here. Coagulation, when we do it, so most of the colloidal particles are negatively charged, okay, in the water, meaning clear particles. Now, in order to make them connect with something, then we need a positive charge, right? So for the electrical neutrality. So aluminum sulfate is the alum, we call it, and ferric chloride. These are the two, they are trivalent, right? Trivalent, Al3 plus and Fe3 plus. If we add them with the water and somehow we can get them separated, means aluminum 3 plus or ferric 3 plus, then they have a tendency to be connected with the negative or sharing, right? 3 negative particles in there, colloidal particles. When they share it, they have a affinity like to come together because of the electrical neutrality and other things. So when they come up with like that, then they become bigger particle, means flux. So that's the process called the charge reduction. Means they have a charge, positive, negative, but when they're coming together, means in this case, what is happening is basically they're staying together, right? And neutralizing themselves. So that's why it becomes that. Coagulation contact of particles. Alkalinity in coagulation needed to neutralize AC4. So that's the main idea in coagulation. I think I have a couple of equations that I can show you that will tell us why alkalinity is very important. So there are key properties of coagulant: trivalent cation, as I mentioned, aluminum or ferric, non-toxic, insoluble in neutral pH. Insoluble means so in this case pH has to go down a little bit, right? So that's why a certain pH is required to make them soluble and make it aluminum free or ferric free, things like that. Okay, here are the process that I'm going to discuss a little bit. As I mentioned, aluminum free or ferric free, both meet the key requirement that we said in here, right? Key requirements are this: trivalent, non-toxic, and this. So these are the two major requirements. So alum, dry or liquid alum, so this is called alum, that can provide is aluminum free, right? The reaction with water containing alkalinity, if I have alkalinity enough in the water, we don't see it. So that means there's some bicarbonate, right? It's a polymer. Then we get aluminum sulfate, carbon dioxide, water, and sulfur. If there is no enough alkalinity, that means these are absent into the water. Then what kind of reaction is going to happen? Aluminum hydroxide, that is solid precipitate, sulfuric acid, and water. In here, you see the sulfuric acid was not there. When it generates the sulfuric acid or creates the sulfuric acid, that the pH will go down. If the pHs go down, what is going to happen? Because we may need to do something else to bring the pH up. So that's why alkalinity is very important in the water treatment areas also, especially if we need to do the population flocculation for the purpose of, like say, bringing the smaller particle, removing the smaller particle. So that's supposed to. That's the importance of alkalinity that I mentioned before. So iron is ferric chloride or ferric sulfate. In this case, ferrous sulfate or ferric chloride. I think ferric chloride is the one to use. We don't use that because 2+ is not a great resource to use. 3+ is better. Reaction of ferric chloride with water containing alkalinity. You see that we have alkalinity, then it's creating ferric hydroxide, carbon dioxide, and chloride. And here we don't have any alkalinity, right? So then it's creating hydrochloric acid and the ferric hydroxide. This is lowering the pH. Okay, lowering the pH. Lowering the pH is another hassle for us because we have to bring up the pH before we can supply the water to the houses and other things like that. Coagulant aids, pH adjusters, activated silica, clay, and polymers. So these are the one can be used to help the coagulant to do their job better. So if you guys are involved in water treatment or even wastewater treatment, you know, some of them, they use these mainly activated silica, clay, or polymers. I have seen some polymers that use. So how we can do the coagulation flocculation test in the lab? So there is a jar test we do. So jar test is basically we add different concentration of ferric chloride or aluminum sulfate at different dose. Then we do the shaking. Shaking in the sense of like first 15 minutes very rigorously, then 2 minutes, then 15 minutes very slow RPM. Then we settle it down, then we take a sample and we measure the turbidity. So turbidity different concentration. Then we do the alum dose and turbidity. So this is alum dose and turbidity. The pH, basically turbidity, initially pH should be this, depending on what is in turbidity, right? So sometimes when I do the lab, I don't get this kind, but this one is always there. So turbidity versus aluminum dose, the idea of optimizing the dose, right? So when I have a less alum, means I have a lot of turbidity there because I cannot bring them together. And when I start adding those, they come together, become flock and settles. Then beyond that point, it's going up again. Why? Because if I add alum that doesn't have any more of the negative ions to stick with, or bring with, or stay together, then what happens? Alum itself becomes a turbidity. So that's why it's like that. So in this case, if I use this for example, if I use 12 milligram per liter, this will give me the best result. Whereas if I use the 6 now, if I use the even 22, no. So that's why the higher amount of something always is not the solution, right? It has to be optimized. So this, in this case, definitely we are doing optimizing, the same as the dry density, right? Maximum dry density, adding water, different moisture content, optimum moisture content, and other things like that. So here is the one example that I have here. So these are 6 containers. Alarm is 666, but they're using polymer in different rates, and they measure the turbidity. Then the product, okay, turbidity versus the polymer dose, because the chlorine dose, so alarm dose is not changing. So they're changing only the polymer amount. So in this case, they did the curve came out to be like that. So in this case, I would say in between 1.5 and 2. Looks like the dip is, maximum dip is here. 1.8 could be the one. Let's see what kind of explanation we have here. Well, the lowest turbidity is obtained at a dose of 2 milligram per liter. This turbidity is much lower than the turbidity obtained at half of the dose. In addition, the minimum point on the curve may be between 1 and 2. If time permits, I would say it may be useful to run another test. However, since the dose chosen is an estimate, the operator may try 1.5 milligram per liter in the plant and adjust the dose as needed. So I think around 2 milligram per liter should be the optimum dose for that problem. I think the question is, the high alarm dose also cause high pH. It could be, but again, the alkalinity has a lot of things to do here. So, I mean, if there is no alkalinity, then what is going to happen? Then the pH will go down because it generates the acid, right? So, and the alarm dose have some kind of effect, or the common ion effect, to make a pH change a little bit. But not always the true. As I said, when I do the lab, the curve that I showed you, I don't get this curve all the time. I don't get this curve all the time. So that means there is a hard way to relate the turbidity versus the pH. Again, depends on what kind of turbidity we have in there. So, and it has effect, alarm has an effect on that, yes. Alarm has an effect. Okay, now we'll be discussing softening process, how we can soften the water, meaning in this case, the hard water. So what is hard water? By definition, hard water is something, if we have any chemical into the water, then it will not give us easy use. Like say, if I put a lot of detergent in there, it will not give me the foam or leather that I need to clean the clothes or whatever we are doing, or utensils and other things. This is one of the issues. Other issue is, if I have a hard water, then sometimes hard water can give us so a little bit of what is called the stain in the utensils and the glasses and other things. Same as the iron, right? If we know that so in this case, if we use the water with the iron in there, then definitely gives us a little bit of water, staining in the water, right? Even drinking the high concentration of what is called the iron water, it can give you stain in your teeth. So here is it happens. Failure to lather well and formation of scum on the bathtubs, and the result reaction calcium magnesium. So this is a soap. Soap is not basically sodium acetic acid, right? Soap is basically sodium acetic acid. So in this case, if I do here calcium and magnesium are present in the water, it's called the hard water, then soap, then it will replace the what is called the sodium from there. It becomes calcium soap. It's become solid, right? So that's why it doesn't give us a foam or leather that we need. So I mean, we need more detergent in this case to avoid this kind of problem. So that is the main problem of the hardness. But hardness is not something can kill people or anything like that. So here is a little bit of description of the soap. As I said, acetic acid, sodium acetic acid, non-ionic hydrocarbon group, and ionic group. So these are basically the soap group that can have a reaction. There are a lot of chemistry here. So then hardness is defined as the sum of the polyvalent cations, mainly divalent cation. It could be more and things like that. Hardness greater than 150 milligram per liter as calcium carbonate is objectionable. Common water treatment goal is to bring down the hardness to 75 to 120 milligram per liter as calcium carbonate. So these are the one. So natural process by which water become hard. These are the process. I'm not going to show it here. I have this curve to show you how it happens. So basically rainwater comes to the topsoil, bacteria action, carbon dioxide in there. So then it goes to the subsoil. Once the rainwater here and the carbon dioxide from the bacterial action in a topsoil, it becomes carbonic acid, right? H2CO3. So carbonic acid, we have a limestone here that has a calcium carbonate, magnesium carbonate, and adding with this one become calcium bicarbonate and magnesium bicarbonate. Now calcium, magnesium carbonate, bicarbonate, and the cations, all of those are contributed to the hardness of the water. To the hardness of the water. So that's how the water becomes hard. Calcium sulfate, gypsum, magnesium sulfate also contribute to the hardness, but their contribution is very minimum. Mainly calcium, magnesium carbonate, and bicarbonate are the major. Okay, so since calcium and magnesium are predominant in there, it is often convenient in performing softening calculation based on the total hardness. That defined as the total hardness is whatever the amount of calcium there and magnesium there. So if I know how to measure the calcium amount, magnesium amount, if I add them up together, I get the total hardness. But here is a little bit of issue because whenever we measure something, calcium and magnesium, we measure them milligram per liter as their ion. Same way we are saying that if I measure two different things, two different units, let's say I measured a height of a student or height of a person is a 5 feet 8 inch. Other person I measured the height is 200 centimeters. So what would be the total height? So how we do things like that? In this case, we have to convert one to another, then add them up, right? So similarly, in this case, calcium and magnesium, when we measure their concentration, we measure milligram per liter as this cation. But when we add them, they are not right because the milligram per liter as ion or as things like that. But we have to bring a common units. The common units is we can convert those milligram per liter as calcium carbonate, both of them, calcium and magnesium, then add them up together. Whatever we get the total, we'll calculate total as milligram per liter as calcium carbonate. So that's why just adding them together is not the right way to do it, but I'll explain more later. Total hardness is also defined as calcium hardness and bicarbonate, a non-carbonate hardness. Carbonate hardness, sorry, this is carbonate hardness and non-carbonate hardness. And carbonate hardness is associated with the bicarbonate, and non-carbonate hardness is associated with the other anions, whatever we have. So carbonate is and non-carbonate is anions, and carbonate is the anions for this bicarbonate. That's the major one, right? That gives us the alkalinity. So here is the one that the way we fill together or put together. I will show you some example that I didn't use the sodium over there. I just used from calcium, magnesium, and there's the total. They didn't even add this one here, right? To show the total part of the total hardness. So then this is definitely carbonate hardness, and non-carbonate hardness would be from here to here. So because the total hardness is equal to calcium, magnesium, or carbonate hardness and non-carbonate hardness. So if I know this total hardness, I know this, I should be able to find the non-carbonate hardness. Okay, any questions so far? I'm going very fast, maybe, right? It's like that, so. Any questions, guys, you might have so far? This is I will just show you a couple of examples. You don't need to do anything, but a couple of examples solving for the softening. We'll see that how much lime we need and other things like that. So this would be very helpful in the treatment class. So now we are going to go discuss the lime soda softening. So lime is calcium oxide and soda is sodium carbonate. It is possible to calculate the chemical doses necessary to remove hardness. Hardness specification is based on the following two solubility equations. Calcium mixed with carbonate becomes calcium carbonate, becomes solid and precipitate. Magnesium as a mixed with hydroxide ion and become magnesium hydroxide and become solid and settles. So these are the two solubility reactions that we need to have. The objective is to precipitate calcium as a calcium carbonate and magnesium as a magnesium hydroxide. In order to precipitate calcium, we need a pH 10.3, and magnesium, we need pH equal to 11. I think in the flow chart of this softening plant, I showed you 10.3 to 11, right? So that's the idea, because we need pH at least 10.3 to precipitate the calcium as a calcium carbonate, and the pH 11 for magnesium to be precipitated as magnesium hydroxide. So that means we have to do something over there to bring the pH up, right? Softening chemistry, again, the chemical process used to soften water are a direct application of the low mass action. Concentration of carbonate and hydroxide are increased by addition of chemicals that have the solubility reactions to the right. So then process convert the naturally occurring bicarbonate alkalinity in carbonate alkalinity by addition of hydroxyl ion. Hydroxyl ion causes the carbonate buffer system to shift the right hand and thus provide a carbonate for the precipitation reaction. So the common source of hydroxyl ion is the calcium hydroxide. But if we know the calcium oxide, then definitely what we will have, we can add some water with it and become a slurry, and this becomes calcium hydroxide. So calcium oxide is called the quicklime. We add water, it becomes hydrated lime, and heat exothermic. The conversion process from the calcium oxide to calcium hydroxide is called the slacking, adding some water, right? When carbonate ions must be supplied, the most common chemical chosen is sodium carbonate, that means soda, right? Because we need some carbonate. Because why? Because carbonate can help us to bring the pH up, number one. And number two is it will be like basically settled down. Combined with calcium carbonate, and it will be precipitate. Sodium carbonate is commonly referred to as soda or ash. So the reactions are regulated by controlling pH, as we mentioned that, and these are like 6 reactions. So here is the first reaction: carbon dioxide in the water. So and this calcium hydroxide we provide calcium carbonate. This step doesn't, nothing removes here. Okay, no hardness is removed in this step, just neutralizing in the water to raise the pH. So that helps. Then the second is to raise the pH about 10.3 to precipitate calcium carbonate. To achieve this pH, all the bicarbonate is converted to carbonate. The carbonate then serves as the common ion for the precipitation. So in this case, we have calcium, we have bicarbonate now, right, a little bit, and calcium hydroxide, so ultimately calcium carbonate and this. Then the next one is for precipitation carbonate hardness due to magnesium. So basically what happens, magnesium and bicarbonate, whatever we have, we are adding this, becoming calcium carbonate, and magnesium carbonate and water. So in this case, this will be removed, but not magnesium is removing, because magnesium carbonate is not precipitate, is not a solid. And the next equation, magnesium carbonate is soluble in this case. With addition of more lime, the hardness due to magnesium is removed. More lime means adding this. So that means this hydroxide going back to connecting with that, becoming magnesium hydroxide solid and calcium carbonate solid. So in this case, looks like we have a both removing, right? Calcium, magnesium both. So then the non-carbonate hardness, as we said, we'll be adding the soda to do that. In order to remove non-carbonate hardness due to calcium, no further increase in pH is necessary. Instead, addition of carbonate in the form of soda is necessary. Then if we have a calcium and we use a sodium carbonate and we are adding this, sodium is okay, sodium plus, but calcium carbonate would be solid and would be removing at the bottom. Meaning it kind of like something like that. The non-carbonate hardness due to magnesium is magnesium and hydroxide again, calcium hydroxide, magnesium hydroxide solid. So although magnesium is removed, there is no change in the hardness since the calcium is still in the solution. To remove the calcium, soda must be added. So here is the soda. So we added soda, it became again calcium carbonate and sodium. This is the same reaction that is used to remove non-carbonate hardness due to calcium. So I think the calcium non-carbonate hardness, we remove this. magnesium non-conforming hardness can be removed by these things. So here are the reaction in one page, all of those without any explanation. And here are the one that we can do during the process. So in these cases, minimum calcium hardness that can be achieved is 30, and minimum magnesium hardness that can be achieved is 10. So that means the 40 should be remaining over there, right? 40 should be remaining over there. Because if we bring it down to this, it's not possible, it's not easy. So you remember the color, because I'll be using some color. These are kind of greenish, right? 30 and 10, probably 40 greenish color. So we'll be using that. Final hardness is targeted from 75 to 120. Things like that. So in order to achieve reasonable removable hardness in a reasonable time, minimum excess of 20 milligrams per liter of calcium hydrochloride must be provided. This is kind of guideline, but the guideline would be there in our flowchart that we'll be using. So these are the one little bit more descriptive stuff, but I'm not going there. I'm going to explain this one. It's exactly the same thing. Initially, I will add the amount of lime, same amount as the carbon dioxide. Then I'm going to add the lime to the same amount of bicarbonate in there. Then I'll go here. Is the magnesium is greater than 40. I know the magnesium amount. What about the amount is in our problem? I mean in our water. So then we'll compare with it. If it's greater than 40, then we'll go to the right. If not, then go to the left. Then add lime equal to 20. Come back here. Then goes to is the non-carbonate hydrogen needs to be removed. If yes, do it. If not, then do it. So this will be very simple. If we have a magnesium is less than 40 or equal to 40. However, if the magnesium is more than 40, then we have to add another line in addition to the top two, in addition to these two. And this amount would be magnesium minus 40. Okay, then done. We have 3 steps here. Then we'll come here. If the magnesium minus 40, after 40, whatever is this, is it greater than 40? If it is yes, come here and do 40 and go down here. But if it is no, it's not greater than, then check whether if it is, check whether it's less than 20. If it is less than 20, yes, then come here, add 20, then go back. If it is less than 20, no, then come here, add another amount, the same entry is here, then go down. So in this case, if I come this way, 1, 2, 3, 4, right? Or even if I go 1, 2, 3, then here 4. I think this would be 4. So either way would be 4 of them addition. In this way would be 1, 2, and 3. So we remember that. If we go to the right side, then 4 would be adding the line, but this would be 5th one anyway. And in this way it would be 3rd one, right? In this way it would be 5th one. This way would be 5th one. Okay, as I mentioned that the conversion that we have to do to make them the same unit before we can start adding them up or things like that. Okay. So milligram per liter as calcium carbonate, if we want to convert it, then milligram per liter as species and multiplied by the equivalent weight of calcium carbonate divided by equivalent weight of the species. So that's what we do. So an equivalent weight is basically atomic or molecular weight by N. We have learned that before, right? N is the value of N, 2 things like that, 2, 3, whatever it comes up to be. But in this case, definitely for calcium, N is equal to 2. Okay, so I have one example problem. Convert the following ion concentration to milligram per liter as calcium carbonate. The calcium was 103, magnesium 505, 5.5, 16, sodium 255 bicarbonate, and chloride is 37. The way I did it, these are the milligram per liter as ion. The equivalent weight of calcium carbonate is 50. How come it is 50? Calcium is 40, right? Carbon is 12. 40 plus 12 is equal to 52. And oxygen is 16. 16 times 3 is 48. 52 plus 48 is equal to 100, right? 100 divided by 2, because we know the N value for calcium carbonate is 2. We explained over here. So that's how I get 50 here. And the molecular weight of the ion, calcium is 40, as we said, magnesium is 24, sodium is 23, I mean 22.98, bicarbonate is, hydrogen is 1, carbon is 12, this is 13, 13 plus this one would be 48, so that's what would be 61%, chlorine is 35.45. The balancing or N value, I put it it together, this is 2 plus 2 plus 2, this 1 plus 1 plus would be 1. So it will be very simple. Equivalent weight of the ion would be equal to what? In this case, would be, this one would be 40 by 2, 24 by 2, and this would be this by 1, this by 1, this by 1. These are the ones. Now, equivalent weight of calcium carbonate divided by equivalent weight of ion. That means I'm doing this divided by this. I got 2.5 this. Then ultimately, this column multiplied by this column will give me the milligram per liter as calcium carbonate. So this is the one. Now I should be able to add 258 plus 23, whatever it becomes, right? It would be 261. But in this case, I should not add 103 and 505 to come up with a total hardness for this. It should be 261, not 108.5. So there are some differences. So I'll leave this in a slide for a minute for you guys to take a look and see whether you have any questions. I'll give you 1 minute for this problem to take a look and see if you have any questions. Okay, looks like no question. Oh, there is a question here. Would excess lime react with sodium carbonate? Again, sodium carbonate, excess lime, not really, because whenever we add the lime over there, it's almost gone. So in this case, we use the soda basically at the last stage in there. So we use the soda basically in the last stage. So that's why excess lime, whatever we add, most of the time, that's the reason we do the calculation, right? We don't use really excess one. So it would be really abundant there and hamper the process. So that could be another options. And the addition of in the flowchart showing excess lime is basically most of the lime we have, they may not be in the good quality or grade. So this is for a safety factor. We use the excess lime to make sure that we have enough lime available for that. But to the best of my knowledge, I don't see any like real interference of the lime with the sodium carbonate, because this is calcium hydroxide. The other one is sodium carbonate, hydroxide and carbonate and sodium, and over there is calcium. Okay, so now let's try to solve this problem. So this is, we'll be trying to find the values of lime and soda, amount of lime and soda to bring down the hardness of the water. So we have a water, and we would like to bring down the final hardness to 78.0 milligram per liter as calcium carbonate. The ion concentration recorded below are all in milligram per liter as calcium carbonate. So it's showing here the calcium 120, magnesium 30, bicarbonate 70, carbon dioxide 10. All of those are milligram per liter as calcium carbonate. Means we don't need to do the conversion, right? Already conversion is given to us. So now we can probably try to do that. This is the flow chart that I do usually to solve this kind of problem. So in this case, carbon dioxide would be to the left side, 10, 10. From here to here, 120 is the calcium. Then 120 plus 30 is 150. From here to here would be this thing. And in the bottom part that we do 0 to 70 would be our bicarbonate. And so in this case, from 70 to here, 150 would be our non-carbonate hardness, right? Because the total minus carbonate hardness would be the non-carbonate hardness. So initially what we do, if we go back to the flow chart, then carbon dioxide does not contribute to the hardness. The total hardness would be 120 plus 30 means 150. You can just take this number. And the carbonate hardness is equal to 70. We already have it. And non-carbonate hardness initial, we put initial because this will help us to, in the sense of doing the problem solving. Total hardness minus carbonate hardness. Total hardness is 150 that we got from here, right? 150. And carbonate hardness is 70, is a kind of light blue color. So this minus this is 80 color. This is olive color. Because I put a color, there is a reason for that. So I know how to use it, why to use it. So remember that this is 78, right? It's a dark brown, or what do you call it? Not the brown, right? Reddish. This is kind of reddish color, maybe. And this one is the olive color. This is a greenish color. And also we have to remember that we have 40, also a little bit of dark green, right? So then we'll be doing the step. This came from the, so this step came from the flowchart that I showed you. So first line is amount of carbon dioxide in here is 10. Then the second line is bicarbonate is 10. The line magnesium minus 40 is equal to negative 10 because it was 30, right? Magnesium was 30. So if I do magnesium 30, the magnesium is greater than 40, it's no, right? So add line is equal to 20. That means we are going to the left side. So 20 means this has only three in there, right? 10, 70, and 20 would be 100 milligram per liter. Meaning in this case, this water, we need line-wise, we need 100 milligram per liter as calcium carbonate. So if I convert into as ion itself, so or as calcium oxide itself, it becomes 56. The calcium oxide has 28, calcium carbonate has a 50 in equivalent weight. So that's why it's 56 milligram per liter as calcium, right? So if we have a 5% impurities in there, then it would be 56 times 1.05, 58 milligram per liter with the 5% impurities. So equivalent weight of calcium oxide is 56 by 2 equals 28. So that's what I got 20. So it looks like there is a question. Let's go from Robert there. Sorry, gentlemen, must close and go to another appointment. Your talk is fantastic. Okay, sorry about that. So it's 11:36. Okay, it's not a question. It's somebody's comment. Then the amount of non-carbonate hardness that can be left into the system. So is 78 or things like that. As we said, we can bring it down to 40. You remember this 40? So this 40 is the one that we said 10, right? We can remove 10 for magnesium hardness, and calcium hardness is 10. Total should be here. So we can bring it down. So we have to leave it there. So we can left into the system, or it could be the final, right? Or NCF final. 78 is the one we would like to bring it down, and 40 should be there, 38, right? We need to bring down 38. Now, the NCS that must be removed, his initial was 80. You remember the color, right? So you remember the color in there, and 38 can be left into the system. So how much we have to remove is 42, right? So then in this case, if we go back to the flowchart, we said whatever the amount is non-carbonate hardness we have to remove, that's the amount, same equivalent amount we have to use the soda, sodium carbonate. So amount of sodium carbonate that we need is 42 milligram per liter as calcium carbonate. So that means then we are converting into as sodium carbonate. So in this case, 42 times 53 by 50. 53 is equivalent weight of sodium carbonate, and 50 is the equivalent weight of calcium carbonate. So basically, we get 44.5 milligram per liter. If we have a 3% impurities, then it would be total 46 almost, right? 46 milligram per liter as sodium carbonate with 3% impurities. The equivalent weight of sodium carbonate, 106 by 2 equal to 52. So that's how I got 53 here. So molecular weight divided by N, right? In this case, N value is definitely 2 for sodium carbonate also, because we have 2 sodium here. Okay, so any questions on this problem? So I'll keep it for a minute. For any questions, I can go back to the slide and come back to that and things like that. Okay, move forward. This is the second problem, the similar way. In this case, we would like to bring it down to 70. So I did two because of the different numbering system. So in this case, carbon dioxide is 17. Again, everything is converted to milligram per liter as calcium carbonate. The reason I'm doing it just to show how it works if the magnesium is greater than 40. The first problem we did, magnesium is less than 40, right? So then we did something like that. Now this one is magnesium is more than 40. So same concept, same process that I'm going to use. Total hardness is 295, carbonate hardness is 265, then initial non-carbonate hardness would be 30, right? In this case, olive color. I'm using the same colors. So then again, lime is the same as 17, carbon dioxide, lime amount is same as carbonate. Then the lime is magnesium minus 40. Since the magnesium is greater than 40, yes, then add lime is equal to magnesium minus 40 to the 35 milligram per liter. That means this color is coming here. Then we are not done yet. So magnesium minus 40 is 35, right? Then we'll go, is magnesium minus 40 is greater than 40? Then it says no, right? When we follow the arrow sign for the no, then it's asked again, is magnesium minus 40 is greater than 20? Then no. Then if we follow the no sign, then it goes here, add the line as magnesium minus 40 again. So this 35 is 35. They are not the same, but two different steps. If I add them up together, it becomes 352.0 milligram per liter. So how much lime I need? For per liter of the water to trade, I need 352 milligram. So again, this is converted into as calcium carbonate. We may need to convert into as ion itself or as calcium oxide, but I didn't do in this problem, but I did in the other one, just to show you how to do it. The amount of NCAs that can be lapped into the system is 70. We want to bring it down 40. We can bring down 40. So how much we can lap to? 30, right? 30. So can be lapped in there is 30. So how much we can remove now? So since we have a non-carbonate hardness and we can leave non-carbonate has 30, we had 30 before olive color one, right? This is the olive color over there, and this is the one. So ultimately it's 0. That means in this case, whatever we can live with, that much we have. So in this case, we don't need to remove anything. That means add no soda. In this problem or this problem solution looks like we didn't need any soda. We needed only lime. Okay. The other way to remove the hardness is the ion exchange. Ion exchange, the way it works, ion exchange resin or ion exchange membrane. So if I have a membrane that has a sodium, and if I pass the water through it, it can replace the sodium with magnesium and calcium, and the sodium can be released to the water, and the magnesium and calcium ion can be captured. So that's the main idea of the ion exchange. So I think I have a little description over there. You guys can take a look. Then the reactor is something that we have that we use to do a kind of reaction, right? Any treatment process or anything other than this, it doesn't mean. Now, reactor could be different types, completely mixed, plug flow, and other things. We know how long the water should be there depending on this hydraulic radius, hydraulic detention time, the V over Q, right? The velocity of the flow divided by Q will be at the time. Mixing and flocculation. Flocculation requires a little bit of mixing, as I mentioned before. So the mixing can be done with the jar test and other things through the paddle. That is like that. During coagulation softening, the chemical reaction that takes place is in rapid mixing form precipitates. Either aluminum hydroxide or iron hydroxide form during coagulation, while calcium carbonate and magnesium hydroxide form during softening process. Coagulation process looks like aluminum hydroxide or iron hydroxide forms, and for the coagulation, and for the softening process, looks like calcium carbonate, magnesium hydroxide formed during the cycle. We see that these are the two definitive for what? Definitive to be precipitated. Again, I think these are kind of duplicates thing. We already said that before. So here are some of the pedal, like say, chamber, different chamber for coagulation, flocculation. So they have a pedal that can move it, and they have a water. Yeah. So this one has a pedal, with maybe moving around to mix those. Some people they use the what is called the buffet valve to mixing them, right? I don't think I have any picture for the buffet valve. Okay. So any questions so far, guys? Okay. So sedimentation, next one we'll do sedimentation, a little bit of description over here. So here's the way it works, like water goes this way coming into the tank. So here is the target buffer, means we have a lot of water going this way. This is the called inlet zone, right? Water goes this way, then the most of the settling part of it, it settles, like the what do we call it, bigger stuff, or even flocks settles here. Then from here, water goes out with the weir, goes out. So this is called outlet zone, this is called settling zone, this is called inlet zone, right? So there are a few things. And this is called the sludge zone. Means sludge here basically settles, then we can probably pump over here. This is the, like say, what do we call it? Sump, right? Sump, and we can pump it out from the sump. Now, sedimentation process basically works the way it is, the resultant force, right? In the statics or simple classes, what we discuss is that how the two forces can be combined together and make a resultant force, right? If a force is going this way, otherwise down, so it may be, like say, it will be coming this way, right? Diagonal. So going down is the settling velocity, and the other one going to the right is the flow velocity, the water is flowing through it. So I think I may have some picture here. These are the description of the settling zone, different zone. There are other things like that. This is the weir, V-notch weir. This example shows a little bit how to calculate the weir length and other things like that. Okay. So this should be the way to calculate the amount of length we need for those things like that. It's not very hard, but very simple example. Then the sludge zone and coagulation flock. Sludge zone is basically, we have to provide a depth for that during the design process. I'll show you an example if we have enough time to show what there is. So there are more ways to calculate the overflow rate based on the height or the depth of the water and the hydraulic retention time. This is hydraulic retention time, theta. H is the depth of the water, V0 is the overflow rate. So here is a more example problem, how to calculate that V0 overflow rate, detention time from the depth of the water and the overflow rate, right? So showing here, and ultimately it was 2 hours. So this is further concept of sedimentation. This is the overflow rate, V0, and Vs is the settling velocity. So one is pushing out, other one is pushing down to the bottom of this thing. So compared to this, I think that's what it is. The V0 is going up, Vs is going down. So that's why the water is coming this way, water is getting out this way, that way. So there are some, here is the one I want to show you. Basically, this water is flowing this way, settling velocity is pushing this way. So ultimately it might take this path, right, for the resultant purpose. So this is a good one, looks like. This is V0 by 2, V0 by 2. But this is escaping a lot of stuff. Here it is not, here it is good. I think this is the one that we should be using. More example. This is a good one. This is our design, but this is under design, right? This is under design, our design, this is design. So we have more problem based on the overflow rate, overflow velocity and the settling velocity and so on. Okay. So I'm not going to discuss that. Then the settling velocity, we can calculate the settling velocity using the Stokes law. I think I have a Stokes law over here. Basically, this is the Stokes law. Vs settling velocity equal to g rho is mass rho over d square by 18 mu. Here is the use of mu. Mu is the dynamic viscosity of the water. So viscosity is important for certain calculation in there. So we discussed the properties, physical properties in there before. Right? Terminal settling velocity ds. There is a way to calculate those. Stokes equation is one of them for individual. For type 2, I don't think we can use that. So there is another way to calculate that. We call it column study. I don't have it here because it's too much materials. But we can do some kind of column study to measure the settling velocity. Here is the, I think, this is the column test results. But I don't think I can use all of this now to tell you how to do it. So here is the jar test that we do for alarm test, right? Alarm dose or other things like that. Terminal velocity, basically these are the one. Round rectangle circular. Gravity removal rate is this, and the outflow solid removal rate are those. These are kind of things. Here is the one, it shows the salination. This is the round one. Basically, these are the trap or weir, we can say. The water is clean in the top because settling in the bottom. The water overflows to this, and this water gets collected for the next step, for next treatment process. So here is the one. I usually take my students to different water treatment plant. This is the one I think I took it sometime. This could be from Nigeria. Looks like Nigeria. But I took some pictures in there. They look very similar. So in this case. So here is the one. I had it from the wastewater. I'm not sure from the water. Okay. Settling tank design, how we can design it. Common land to width ratio 2 to 1 to 5 to 1. Land should not exceed 100 meter, and the depth should not exceed 5 meter or so. Things like that. Column tests are performed to find the optimum detention time and overflow rate. So overflow rate and detention time, I don't know, but we have to do the column test to find those. But the literature has different values that we can use. So I think I have a picture here. This is the table. So for this is the range, these are the typical values for the overflow rate. We can use for average flow is 40, peak flow is 100. Average flow again is for 30 and 60. So you can decide from here which one to use. Okay, this should be calculated based on the engineering judgment. But this can give us an idea. This is also another one. So the detention period, to find the detention period from the column test. Looks like in this case, they found something for the 40 overflow rate with the test, 2.7 was the value, 2.7 hours. Right? So 2.7 hours. But there is a column test. If we do it and plot it, we should be able to calculate it. But in this case, we don't need to do it. Let's try to solve this problem. This problem would be very useful for the sedimentation tank design with the surface area and other things like that. We don't have that much of time. Determine the surface area of settling tank for the city of Richmond. So 0.5 meter cube per second design flow using the design overflow rate of 32.5 meter cube per meter square. Compare the surface area with that, which results from assuming a typical conservative overflow rate of 20. Find the depth of the clarifier for the overflow rate of 32.2 meters cube per meter square, and the detention time 95 minutes for a length. 4.5 is 2. And the maximum length is 100 meter. Maximum depth is 5 meter. Provide minimum 200. So I'll leave you for 30 seconds to read the problem. So you know what kind of problem we are solving. We are designing a sedimentation tank, right? With the surface area. We can do the depth also. Here is the design. We convert this one into meter cube per dam. Overflow rate is this. Overflow rate is this. Conservative one. Detention time is this. So settling tank surface area would be Q over V. So Q is this. V over this. Q is this. V over let's say 32.8. Let's use this first. We get 1329 surface area. If I use the conservative one, overflow rate 20, then I get 2160. How more we are providing using the conservative estimate? Surface area is almost 62.5% higher than the area. So you see that a little bit of change in the overflow rate that can give you very higher requirement of the surface area. So the surface area almost 62 and more. The design surface area for the tank is this. The volume of the tank is Q times T is this. Then if we calculate the tank depth, so it would be 2.4 meter, things like that. Surface area of each tank would be this. If I provide two tanks, the problem says that provide two tanks, then surface area equal to L times W equals 4.5 W square equal to this. From here we can calculate the W, 12.1, and L equal to 54. So this W doesn't have any requirement, but L has a requirement of max is 100 meter. So this is less than 100 meter anyway. That should be good, right? So dimension would be, for this case, 54.68 is the land base, width is 12.15, and depth is 2.14, right, or 15, and plus freeboard plus large depth. So if the L max requirement is not met, increase the number of tanks and calculate the L and W gain. So it could be a trial and error method, right? So I will leave this problem there for a few seconds. You guys can take a look. Okay. So here is another problem we would like to solve again. You are asked to design a water treatment plant settling tank, length, width, depth, and check the volume provided. After calculation for the city of hostel, the design flow is 0.85. The overflow rate, retention time are this, respectively. City hostel keep the 50 meter, and the length is just 4:1. I think I have the solution here. What I did here, I did the surface area. Then I did the total volume required is 4819.5 meter cube is the surface area. And in this case, depth would be volume by surface area is equal to 2.3 plus depth plus freeboard we have to provide. Then the second part is number of tanks. I put 1 in there first. Then if I do the calculation, looks like I got 22 and length is 91. So it's not right. Then I did the rough calculation, how many tanks I need to meet this requirement. Looks like 8. So if I put 8 over here and do the surface water calculation, then I get this. Then if I do W calculation, same way that I did, 8.1, and L would be 32.39. So this is less than 50. This doesn't have any requirement. And the depth is what? I think we already did the depth, right? Depth is we consider 2.3 meter. We already did depth is 2.3 meter. Liquid depth. Okay, so I got it run. Then that means in this case, I got this, the volume provided is the same as volume needed or a little bit more. Then it is acceptable. So here is some note. In practice, even number of tanks are provided. In this case, you can provide 8 tanks. If the number is odd, then open one, add one more tank easily with a smaller size maybe. Okay, filtration, again, filtration in order to remove the particulate matter, right? Suspended solid and other things. So here are some of the requirements. There are initially based on the media, two-type, dual media, mixed media, based on the allowable loading rate, how much you can do per minute per hour, slow send filter and rapid send filter or high send filter. There's the definition of slow send filter, rapid send filter. Mainly, the loading rate is 2.59 to 7.6. Here it is 120 to 235. So here is the sedimentation tank. These are trapped. There could be something in the bottom. Put in a like say, sand and the anthracite here. So here is the other one. Looks like this is full of water. It's passing through. I mean, it's filtering. But the top order looks like very clean. So here is the backwash for that. Fraction of efficient filter, backwashing. So how I can backwash. So dual media means it has a multiple media, two media at this side. The loading rate is 300 meter cube per meter square. Then the deep bed looks like 800 meter cube per meter cube per meter square. So these are the one with descriptive. Grain size distribution, this has to be kind of uniform, coefficient or things like that. It's well graded, right? Mainly well graded. We don't want to say anything that is not well graded for that. So there has to be some design. I think uniformity coefficient is basically 1.3 to 1.7 is required for that. And the 10 effective size, B10 is 0.35 millimeter with a maximum 1 millimeter. So here is the loss we can calculate, and based on the loss, if we see based on the calculation 0.6 or more, then we have to start cleaning the things like that. What kind of cleaning? Backwash, right? Because it may be clogging. So here is the 1.6 meter. Initial head losses in excess of the 0.6 meter indicate that either the loading rate is too high or the sand has too large or fine grain sizes. And how we can calculate the 0.6? 0.6, if the depth is we provide, like say, our design depth is 6 feet on top of the like say, the filter unit. Then after some time we see, calculation shows that we have a excess delta H or whatever we can call it, or people that is HL is 0.6, meaning in this case, it will be 0.6 meter means like say what, almost 1.5 feet, right? 1.5 would be stagnant there. 1.5 feet would be stagnant, meaning in this case, either if it is existing one, then we have to do basically what, like say backwashing, or if it is the initial calculation, then definitely we have to see, okay, we have to change the gradation of the sand and other things like that. Disinfection, as I said, disinfection to make the water potable means safe to drink, right? Mainly killing the bacteria, virus, amoebic sieves, and other things like that. So it's done by a different way. One is called the chlorination and other things. This one is also follow the first order kinetics. I think we discussed the first order kinetics, right? Number of organisms destroyed in a unit time proportional to number of organisms remaining. This is the first order kinetics. So the first order reaction N equal to N0 to the minus KT. So from here, if I know this amount and I want to go this amount to be almost 0, then definitely I know what would be my time, right? How long it will take, or what is the rate of the kill per unit time, how much I have to kill or things like that. So bichlorine, basically provided by sodium hypochlorite or calcium hypochlorite or chlorine, then sodium hypochloric acid become hypochlorous, right? This is hypochlorous and this is chlorous, hypochlorous. And if I do that, ultimately chlorine comes here. Now, the two different form of chlorine can kill different kind of bacteria. This chlorine, hypochlorine, and hypochloric is hypochlorite, and it is a hypochlorite here too. Hypochloric acid, I think. This is hypochloric acid, this is hypochlorite, and this is just chloride. All three are capable of deactivating the or deactivating the microbe or leaf, what is called the cell of the organism. So we need to wrap in a few minutes. Okay, so we can do it. I think we started at 13 minutes late, but that's fine. Let me see, I have a few things just to browse those, then we'll finish it. So here is the disinfection by chlorine a little bit more. Chlorine byproduct gives me trihalomethane, THM. Okay, so here is the one, how we can do, how long time we have to have the chlorine in contact to make sure that we achieve whatever we need to achieve. So here the removal rate, 3 log is 99.9, 4 log is 99.99, that we have to do for certain parameters. So here are some of these calculations you can see. Some of the example problem I have, if we do the calculation, we can compare with this to make sure that we have enough contact time to do the disinfection process. Okay, so these are very good to read. Whenever you guys have time, you can read those. Disinfection by ozone is another way to do it. And the last one is infection by ultraviolet radiation, means through the light and other things like that. So here are more showing that. You guys can take a look. Absorption is another process by observing different materials or ions with the carbon. Then it's called the absorption process. It's surface phenomena. They can pack at the two-way to do it, granular activated carbon and powder activated carbon. There are more description over here. Then the water plant waste management. Basically, sludge is the major waste in there. As we have seen, like especially sedimentation tank, there's a lot of sludge, as well as the precipitation tank, right? As well as the softening tank, there's a lot of sludge. So these are the sludge we have to manage differently. Okay? So a liquid and solid and liquid sludge, there are different ways that different types we can have. Here are the liquid phase and the gas phase that we can do. And finally, sludge management comes to following approach: minimize the sludge generation, chemical recovery, sludge treatment, ultimate disposal. It could go to the landfill or some other way. So here are some of the calculation we can use to know which part creating how much of the sludge mass-wise, so we know how much to depict it. EPA, there is a question here. Is EPA pushing for non-chlorine type disinfection technology? Yes, it is for the wastewater. Definitely non-chlorine is more prevalent and more useful. But for the water, yeah, you can do it, but still there is a chlorine required because of the chlorine has to be in the water as a persistent. If there is a cross-connection, cross-contamination happens, so that residual chlorine in the water before it goes to the individual houses can kill it and still be safe. So that's the only difference between these two. Yes, EPA non-chlorine type disinfectant is better for the wastewater, but not for the water. Okay, so there are some of the equation we can use to find the amount of sludge to be generated, so we know how to do it. These are different processes: sludge thickening, sludge treatment, and dewatering. Then finally, it goes to the food disposal with soil sludge, landfilling, and land spreading. It can go anywhere. Here is the summary. I don't think we have enough time for those. These are the ones that I explained what we did in here. I think it says we solved several problems on coagulation, calculation, limestone, sedimentation tank design, right? As I mentioned before, that we'll do a little bit of design. We did a design sizing at least 2 tank, right, in there. And that's it. Here is my email address. For anything you need to contact me, you can contact me with this email address. I think the slide will be with Hisham will have the slides. So you guys can probably get it from there, or you can email me. I can send those to you too. So it's not a big deal to do it from my side. But Hisham said he will have it with this thing. So I will stand by for a minute or so. If you have any questions, please feel free to ask. If not, then we are ready to close this session. Thank you guys for listening, and I'm sorry for the technical difficulties in the beginning for losing 13 minutes. I do apologize seriously from my side. Okay, well, probably we can, Hisham, do you have anything to discuss, or we can probably, uh, most of them are gone, right? Okay, still some of them are hanging. So if you guys have any questions, please feel free to ask. Otherwise, we can. Okay, goodbye.